on Monday, we were looking at what happened if we had an RLC circuit that did not fall easily into the bucket of a series RLC circuit or a parallel RLC circuit. Today, we're going to look at just a simple circuit where we have two capacitors, but because the capacitors are not connected in series or parallel, we can't lump them into a single energy storage element. So it's still going to look like a second order system. And then we're just going to work our way through yet another example of how to solve for that second order differential equation, and then use that to approach everything else. Okay. So our example problem in this case, and I think this is strikingly similar to the circuit that we analyzed on Monday. We've got our voltage source. Here's my resistor R1. I've got a switch that's closing at t is equal to 0. And then here in this branch, I'm going to have some resistance R2 in series with some capacitance C1. And then over here to the right, I'm just going to have some capacitance C2 like so. So if my memory serves me correctly, this is a pretty darn similar circuit, except that one of those capacitors was replaced by an inductor or something like that. So I'm going to go ahead and define some things here really quickly. So let's call the current flowing through capacitor C2 just I2 of T. The voltage drop across capacitor C2 will be V2 of T. The current flowing down through capacitor C1 will be I1 of T. And the voltage drop across capacitor 1 will be V1 of T. So since we have two capacitors here, ultimately our goal is to come up with a second order differential equation, either with V1 as our only variable or V2 as our only variable. If we had a circuit like this where instead it was only inductors, we would be looking for the inductor currents as what our differential equation is going to be based on, right? Okay. So we're going to approach this guy in a pretty similar fashion to we did the other one, because I find it easier to just use KVL, KCL, and Ohm's law than trying to make nodal and mesh fit this thing, which again, it technically can if that's your inclination, but it genuinely makes it harder. So if we were to apply Kirchhoff's voltage law around our right-hand loop here, I think we could easily see that V2 of T is going to be equal to just the voltage drop across R2 of T. So that's R2 times I1 plus the voltage drop across that capacitor C1, which is what I have as V1 of T. And now, much like I did on Monday, I'm going to replace my capacitor current with an expression that has my capacitor voltage in it. So that's going to give me this relationship. V2 of T will be equal to R2 times C1 times the derivative of V1 with respect to time plus V1 with respect to time. So before we move on from here, does anybody have any questions, comments, or concerns about where any of this came from? Fairly straightforward, okay? The next thing I might do is, again, very similar to what we did on Monday. I'm going to apply Kirchhoff's current law at that topmost node, top middle node, essentially. So I'm going to say that the current flowing in is equal to the currents flowing out, where the currents flowing out are just those two capacitor currents, right? So KCL at top middle is going to look something like this. So I'm going to choose to express my current flowing in as Vs minus V2 of t divided by that resistor R1. And that's going to be equal to the current flowing out of that node, which is just I1 plus I2. And now I'm going to rewrite this guy expressing both of those capacitor currents in terms of their respective capacitor voltages. And for what it's worth, I'm also going to move that factor of V2 over R1 over to the right-hand side. So we might have something like this. Vs divided by R1 is going to be equal to 1 over R1 times V2 of t plus C1 dV1 by dt plus C2 times dV2 by dt. So anybody have any questions, comments, or concerns about how I've applied Kirchhoff's current law and then how I've rearranged and re-expressed these relationships? Okay. So if we look at that KCL equation, right, our first term is in terms of just V2. And wouldn't you know it, we have an expression for V2 in terms of V1 up here. Our middle term is already in terms of V1. So really the only thing that we're looking for is what the derivative of V2 is going to look like. Well, that's pretty easy because we can just use this equation and take the derivative of it. So we could say that the derivative of V2 with respect to time is just going to be the derivative of the right-hand side. So that's going to be R2 times C1 times the second derivative of V1 with respect to time plus the first derivative of V1 with respect to time. And so all I'm going to do now is just substitute those two relationships that we got from our KVL expression into our KCL expression. And so that's going to give us Vs over R1 is equal to, 1 over R1 multiplied by V2, where V2 was R2 times C1 dV1 by dt plus V1. Now I just have my C dV1 term, or excuse me, so C1 dV1 by dt, and then C2, and I'm going to substitute in that derivative relationship from above. So that's going to look like R2 C1 times the second derivative of V1 with respect to time plus dV1 with respect to time. And now I'm just going to group things up. So my second derivative term, I'm going to put that one first. So I'm going to have a factor of R2 times C1 times C2 times the second derivative of dV1 by dt. Now I'm going to put all my first derivative terms. So from that very first expression up above, we would have an R2 over R1 times C1. From that middle term, I'm just going to have another C1. And from the right-hand term, I'm just going to have a C2. And then lastly, I just need my 0th derivative term, or just my function by itself. And the only one of those that I have, I believe, is just 1 over R1 times V1 of t. So before we move on from here, did anybody notice any algebraic mistakes or anything as I distributed things out and then lumped them together as coefficient of the second derivative term plus coefficient of the first derivative term plus, coefficient of 0th derivative term? I don't think I made any mistakes, but I usually don't, and I'm wrong. So nobody's piping up that they've seen any mistakes out of me today, so that's great. So the last thing that we would do here is then just divide both sides through by R2 times C1 times C2. So that's going to look like VS over R1, R2, C1, C2 is equal to the second derivative of V1 with respect to time plus, so let's see here. I'm going to pull out a C1, then I'll have a 1 plus R2 over R1 plus C2, all divided by R2, C1, C2, multiplied by my first derivative. And then lastly, I'm going to have a 1 over R1, R2, C1, C2 by V1 of t. And from this second order differential equation, we can say that alpha is just going to be whatever C1 times 1 plus R2 over R1 plus C2 is. It's going to be all of that divided by twice R2, C1, C2, because remember that alpha is just 1/2 multiplied by the coefficient of the first derivative term. And omega naught is going to be the square root of 1 over R1, R2, C1, C2, because omega naught is simply the square root of the coefficient on the 0th derivative term. And from here, if our circuit had, numbers for or values for the components and all of that kind of stuff, we could tell whether it was critically damped, overdamped, underdamped, and then proceed from there. Analyzing at, 0 minus, 0 plus, and infinity, setting up our system and solving it like any other circuit that we've done. So unless you guys want me to throw numbers into this thing, that's really all I wanted to talk about for today. We can spend the rest of the class meeting reviewing for your test on Friday. For what it's worth, I am going to post a homework assignment related to these general second order circuits. It isn't going to be due until early next week, so probably Monday of next week. But since you're not being, the in-class portion of your test is only on series and parallel RLC circuits, I think it's fine with that homework not being due until after the exam, because the take-home test portion is going to be about this stuff. So you'll have time to work your homework assignment before you get cracking on that take-home test. All right, so what do you want to talk about for the next hour? Yes.
When is the take-home portion of the exam going to be due?
So I'm going to assign it to you on Friday, and it'll be due the following Friday. This time, I'm going to try to not be a jackass and actually publish it so that you can see it and we can stick to that schedule instead of not finding out that I forgot to publish it so that you guys couldn't see it until afterwards. Yes. So Which one, do you want to replace both of them with inductors? All right, let's see what happens, just for the hell of it. Apologize for constantly scratching my nose. I don't know what the deal is, but my allergies are just going absolutely bananas now that I'm down in this room. Didn't have any issue in my office at all. So I'm insinuating that somebody's wearing, and I can't smell it, somebody's wearing way too much body spray that I'm allergic to. So let's define the current flowing through this guy as I2. This will be our voltage V2. This current flowing down through here will be I1, and this will be V1. And I'm going to approach this exactly like I did the last problem. Okay. So my KVL equation, I'm going to have V2 is equal to R2 times I1 plus V1 of t. And I'm going to choose to express, or I'm not going to choose now, I need to express both of those inductor voltages in terms of my inductor currents. So that would look like L2 derivative of, sorry, I2 with respect to time is equal to R2 times I1 plus L1 times the derivative of I1 with respect to time. So that's my first equation. My second equation is going to be from KCL again. And so I would have probably Vs minus V2 over R1 is equal to I1 plus I2, where I could make this now look like Vs over R1 is going to be equal to, let's see, so V2 is L2 di2, so that'll be L2 divided by R1 di2 by dt plus I1 plus I2. So what I'm going to do here is I'm going to rearrange this guy and solve for I1. So I would say that I1 of t is going to be Vs over R1 minus I2 of t minus L2 over R1 times the derivative of I2 of t with respect to time. And taking the derivative of this guy, I could also find that di1 by dt is going to be equal to negative di2 by dt minus L2 over R1 times the second derivative of I2 with respect to time. And I'm going to substitute these two equations into this guy right here, and now everything will be in terms of I2. Okay. So that'll give me L2 di2 by dt is equal to, let me just scroll up here. So R2 times I1, where I1 is Vs over R1 minus I2 minus L2 over R1 times the derivative of I2. And then I have plus L1 times di1 by dt. So L1 times negative di2 bless you minus L2 over R1 times the second derivative of I2 with respect to time. And now it's just going to be rearranging things. So I would have R2 over R1 times Vs will be equal to, so my second derivative term, I'm going to move essentially all of those I2 related terms to the other side of the equal sign so that they'll all come out positive. So that'll look like L1, L2 over R1 times my second derivative. Now I'm going to have my first derivative terms. So I can see over here, I've just got a factor of L2. Then from this term right here, I'm going to have an L2 times R2 over R1. And from this term right here, I'm going to have just an L1. And I think the only thing I have left is just plus R2 times I2. So multiplying through by a factor of R1 over L1 times L2, that's going to give me, let's see, R2 over L1, L2, Vs is equal to the second derivative of I2 with respect to time plus, let's see, so I'm going to have L1 plus L2 times R2 over R1. That's going to be multiplied by R1. That will be divided by L1, L2. And then I have my first derivative term. Plus R1, R2 over L1, L2, I2. And so alpha is L1 plus L2 times R2 over R1, all multiplied by R1, divided by twice L1, L2, and omega naught is the square root of R1, R2 over L1, L2. So the setup is essentially always the same. KCL and KVL, and then it's just figuring out which of those equations to manipulate so that you can do substitutions and get it down into a equation, second order differential equation where you only have one variable. Yes.
So would a good rule of thumb for like series and parallel and RLC circuits would be like, if we're looking for current, you start with current, like, inductor current, then find the derivative to find the voltage for an inductor, and then use that to, I guess, find the current of whatever it's asking for.
So I don't know if I would call that a good rule or not. So let me pull up the homework assignment and I'll kind of talk my way through deciding which system of equations I would solve.
Big one for me is like number 5, capacitor voltage, then finding the current through the capacitor, and that ended up not working as well as I thought. So I ended up having to do current, and then voltage through the inductor.
So let's see, spring 2025 homework 7, right?
Yes.
So for this one right here, we're ultimately trying to solve for V of t and IL of t, right? So this voltage V of t happens to also be, not only is it the capacitor voltage, but it is also the inductor voltage. So my first equation would be for IL of t, and my second equation would be for VL of t in this one, because that lets me solve for both quantities with the least amount of work. For problem 2 here, let's see. So ultimately, I'm trying to solve for IA. So if I recognize, and you have to recognize this at some point in order to actually solve this circuit, that this whole thing right here is some equivalent resistance, then I would say the easiest way to solve this guy is recognizing that IA is just going to be V of t divided by Req. So if you solve for the capacitor voltage, so from this equation 1 is VC and 2 is IC. That's the most straightforward way to solve it. For problem 3, let's see here. We're ultimately trying to solve for that current I of t and that voltage V of t. So during the transient condition, this current I of t is also flowing through the capacitor. So my first equation would be VC, and my second equation would be IC. And that gives me both pieces of information that I'm looking for. In problem 4, we're solving for VL and IR. So during the transient condition, I can see that IR is flowing this way. So essentially IR is just negative I of t. So my first equation would be IL, because that is what I of t actually is. And my second equation would be VL of t. That way I get everything that I need pretty easily. This guy right here, if we recognize that this thing is an equivalent resistance, which again, we have to do to determine whether or not it is a, like whether it's overdamped, critically damped, etc. I actually think that IA would be easiest by doing current division, because I know that all of I1 is going to flow through here, and then it's going to split between those two resistors. So my first equation would be for my inductor current And my second equation would be for, sorry, my inductor voltage. And then using these two equations, I could say that IA is just negative IL times 1/3 over 1/3 plus 1/1 is how I solved it. It could be done potentially using the capacitor related quantities, but I'd need to think about it for just a moment.
Right, really didn't work out very well, because B1 and B2 did not exactly match up with, giving the VL to the IL quantity.
Yeah. So I mean, like realistically, if you use the capacitor quantities, I of t is still the capacitor current. So if you can solve for that, you can use that current division relationship. But if you don't do that, that's where it gets significantly more difficult. So let me just think about this real quick. I'll answer your question and just so I'm trying to think about how we could potentially do a KVL around this path. So if we did KVL around that path, right, we would have VC plus VL minus 2IA minus 3IA is equal to 0. Where I'm saying this is the voltage drop across this 3 ohm resistor is that 3IA, right? Actually, hold on. Yeah. So that would be VC plus VL minus 5IA is equal to 0, or 5IA is equal to VC plus VL. But so VC is the capacitor quantity. VL is just L times the derivative of the capacitor voltage with respect to time. And then I would divide all of that by 5. And so that's how I would do it, only in terms of capacitor quantities, but that's way more of a pain in the ass than using current division. All right, Josh, how may I help you?
Um, for the equivalent resistance, why do we care about the dependent source?
Because it exists.
Well,
I mean, that's like, so whenever we're trying to find the equivalent resistance of our circuit during the transient condition, we take our energy storage elements out, which is just these two, leaving behind a network that contains a dependent source connected to two resistors in parallel, and we need to find the equivalent resistance of that dependent source connected to those two resistors in parallel. We can't just throw it away. So we have to consider it because it exists. Yeah. I mean, I know that sounds snarky, but it's the truth. So just as a heads up about your exam on Friday, it will be 2 questions. One will be a series RLC circuit and one will be a parallel RLC circuit. One will have a dependent source and the other one will not. So if you've done your homework, the exam should be a joke. If you haven't done your homework, the exam is going to wreck you. But that's probably true for every exam in this class. So any other questions regarding the homework while I have it open and it's scribbled all over the damn thing? Yes, Kobe.
So for an underdated system that's like in parallel series, how do we find the V1 and V2 things for our YT?
So, so we've got an underdamped system, okay? So we know, let's just say that we're trying to solve, we're setting up our system using capacitor voltage and capacitor current. It's going to be effectively the exact same thing if we use inductor current and inductor voltage, right? So my first equation is going to be, let's just say VC of t is equal to B1 cosine omega dt plus B2 sine omega dt e to the negative alpha t plus VC at infinity, right? So at t is equal to 0 plus, cosine of 0 is 1. Sine of 0 is 0. And e to the 0 is 1. So we're going to have B1 times 1 plus B2 times 0. And all of that is multiplied by 1 plus VC at infinity. So B1 is just going to be VC at 0 plus minus VC at infinity. And if we were using inductor current, it would be IL at 0 plus minus IL at infinity, 100% of the time. Okay. For our second equation here, we know that our capacitor current, IC of t, is C dV by dt. And so we would have C, and then we would just pull this from the table. I'm doing this from memory, so I think it's omega d B2 minus alpha B1 minus omega d B1 plus alpha B2. Shit. I forgot the cosines and the sines there. Sine omega dt, close that e to the negative alpha t. Did I pull that from my table memory correctly? Nobody's saying I screwed it up, so. Okay. So from here, I could say that IC at 0 plus is going to be C times, and once again, cosine of omega dt, or cosine of 0 is 1. Sine of 0 is still 0, and e to the 0 is still 1. So the only thing that's going to survive this is the omega d B2 minus alpha B1. So rearranging a little bit, I believe I will have B2 is equal to IC at 0 plus plus, excuse me, C times alpha B1 divided by C times omega D.
It's after we put everything in terms of the capacitor or the inductor.
Mhm. So if we had if we were doing inductor current and inductor voltage, the only thing that would change would be that would now be VL at 0 plus, and those C's would obviously be L's because we're dealing with inductor quantities. Seneca.
Of a
So in an overdamped circuit, just for what it's worth, let's do it with inductor current really quickly. So we would have IL is going to be A1 e to the S1 t plus A2 e to the S2 t, right? So that means, oh, excuse me, plus IL at infinity. So IL at 0 plus is literally just going to be A1 plus A2 plus IL at infinity. And so from here, our first equation is going to be A1 plus A2 is equal to IL at 0 plus minus IL at infinity. Then for our derivative, which in this case would be our inductor voltage, that's L di by dt. So that's going to look like L times S1 A1 e to the S1 t plus S2 A2 e to the S2 t. So VL at 0 plus is just going to be L S1 A1 plus L S2 A2. So this is our first equation to put in our system solver. This is our second equation to put in our system solver. And then we have to solve that system simultaneously. It's the only one we actually have to solve simultaneously. For the underdamped case, we just showed that, essentially because the sign of 0 is 0, we know that we're going to get to throw that B2 away and solve for B1 directly with that first relationship. And then using that value of B1, we can solve for B2 in the next one. In a critically damped system, we know that we're going to get A2 directly from our first equation, and we're going to use A2 to solve for A1 in our second equation, which if you want me to set that one up as well, it's pretty straightforward. Right. So just generally speaking, I'm just going to do this one in terms of, actually, I don't want to do it in terms of Y, because I don't want you to forget that you have to include the capacitor value or the inductor value where appropriate. So if we say that VC is A1 t e to the negative alpha t plus A2 e to the negative alpha t plus VC at infinity, then VC at 0 plus is going to look like A2 plus VC at infinity, since A1 times 0 is going to make that first term go to 0, and e to the negative alpha 0 is just going to look like 1. So from here, we could say that A2 is just VC at 0 plus minus VC at infinity. And then let's see, our capacitor current is going to be C, and then let's see, I don't remember this one. Somebody let me borrow a table real quick. I don't want to do gross derivatives in my head. Thank you. Negative alpha A1 t e to the negative alpha t plus A1 minus alpha A2 e to the negative alpha t. Thanks. So IC at 0 plus is going to be, so that whole first term is going to go away because I have a t down here since it's 0, that guy dies. And so I'll just have C times A1 minus alpha A2 is equal to IC at 0 plus. And so rearranging this guy and solving for A1, I would just have A1 is equal to IC at 0 plus alpha A2, excuse me, C alpha A2 all divided by C. And now I've taken all of the thought out of doing literally any of these. you can now just literally just straight up apply this stuff 100% of the time to figure out what any of your coefficients are, and then it's hopefully just a very small amount of circuit analysis at the very end to just answer what I'm looking for.